Okay, guys, let's kick this off with heat and temperature, which is going to be the first topic we will cover in these Unit 5 videos, okay? So heat and temperature. Before we say anything related to physics, I'm gonna mention one thing that I find important to both me and thermodynamics as a field. Thermodynamics and its development led to the first industrial revolution from history, okay? So first industrial revolution was due to thermodynamics. So this is when human beings started developing machines, and these machines were steam engines and stuff like that. So understanding thermodynamics was important from that point of view as well, okay? So all these things were studied about 200 to 300 years ago, okay? So let's define what heat is to begin with. So when heat, which is a form of energy, so form of energy measured in joules, okay, is provided to a substance, and this substance is usually a solid, a liquid, or a gas. So these are the three most popular phases of matter that we will deal with in this chapter, okay? So when we provide heat to a substance, its temperature measured in degrees Celsius or kelvins rises. Now, what is temperature? So temperature is pretty much related to motion, okay? So it's a form of energy in some sense, but it has to be multiplied by something to become an energy. And that something is Boltzmann's constant, and we will talk about that later. But for now, let's write down the temperature. Temperature signifies how cold or hot an object is, or a substance. So an object or a substance is, but internally. So if we look into the internal structure of the object, but internally it tells us how fast molecules vibrate. So temperature tells us how fast molecules vibrate, and this happens in solids or liquids, or how fast molecules move, and this is in gases, okay? So let's talk about the internal structure of things. So let's take solids, okay? So I'm gonna use, I hope this makes sense. Let's draw a box that is supposed to be a solid, and let's use red to signify, let's say, negative ions, and blue to signify positive ions. So red is negative and blue is positive, okay? Plus Q. So this is gonna take time, so anyway, let's do one more row. Okay, now this is the situation in solids. So you can think of, for example, salt, NaCl, right? So sodium has a positive charge because it loses one electron, which goes to chlorine that is negatively charged, okay? So in a solid, these two ions, red and blue, are closely packed, so this is a tightly packed situation, and the electric potential energy is given by minus K Q, let's say Q1, Q2 over R. Okay, so let's call this, let me erase this, sorry guys for the confusion. So let's name this Q1. So we said that this is the negative, so minus Q1, and we said that blue is the positive, so plus Q2. Okay, so the electrostatic energy is negative and R is very small, so let's R is the distance, so R is this distance between a positive and a negative ion, for example. Okay, so this is very large in the negative sense. Okay, hope this makes sense. If it doesn't, let me know in the comments. Now let's go see what solids look like. So not solids, liquids. Okay, I'm gonna use the same ions as before, and now we will have a situation that will look like this, for example. Okay, these are my positive ions and these are my negative ions. They are still there, this whole thing is still bound, but R, the distance between a positive and a negative ion, is larger. Okay, so in a liquid it's still bound, and V is also minus K Q1 Q2 over R. But since R is larger, so this R is larger than the R for the solids, so the potential energy, the electric potential energy, is still negative but larger, so smaller. So in the sense, let me use numbers. So if this is if we set everything to 1 except R, then this is minus 1 over R, and this is also minus 1 over R. If R is 0.1, then this V is minus 10. But if R is, say, 0.5 larger, then V is minus 2, right? So this potential energy in a solid is larger, but in the negative sense. Okay, it's more negative. It takes more energy to break these bonds. This is what larger potential energy means, pretty much. So, and it's much smaller in liquids. The last one we need to talk about is the gas. So a gas is not bound at all, but let's assume that there are some walls that hold it together. Now I'm gonna have my positive ions and my negative ions still, but there will be no structure, and this distance R, actually let's draw it from here. So this distance R is much larger, so V is approximately equal to 0, because it's still minus K Q1 Q2 over R, but since R is large, V is approximately equal to 0, and in gases atoms or molecules are free to move. Okay, so that's the situation. And also we silently assumed that in going from solids to liquids and then gases, we increase the temperature. Okay, so the temperature increases as you go from a solid to a gas. Okay, we haven't done this in a while, but let's see these phases, as they call them, of matter using this simulation. So in this simulation, we see water, which is frozen because the temperature is 146. Let's turn it into Celsius actually for now. So it's minus 127 Celsius. So we see how this is actually a solid, okay? We can also turn this into liquid. So this is 13 degrees Celsius, and into a gas, okay? So here is a solid. You have tightly packed molecules close together and they vibrate. In a liquid, they still vibrate, but they have a larger range of motion, and the whole thing is bound, meaning that no molecules escape from the rest of the molecules. But in gases, they do escape. So let's go start with a liquid and heat this up, okay? So it's 13 degrees Celsius, and we know that water boils at 100 degrees Celsius. So let's boil it up. So the temperature increases, as you can see, and now we hit 150 whatever degrees Celsius, and this turns into a gas, guys, you see. And the more I increase the temperature, the faster these molecules move. Okay, let's see how far up I can go in terms of temperature. I still hit this thing up, and you see how things go bananas. They go crazy. Okay, molecules move really, really fast. They collide with each other, etc. So this is the gas phase. Let's cool it down. Let's go in reverse. It's still a gas. It's gonna take a while because I increased the temperature by too much. Actually, let's press the liquid phase, okay? And let's cool this down. Okay, see what happened there? So this is a liquid, right? 5 degrees Celsius, and now 0 degrees Celsius is ice. And if I go a little bit down, you see how this is now a solid. Okay, tightly packed, and these guys move really, really fast. I'm wondering if I go to minus 273, let's see. 273 is known as the absolute zero, and every motion stops at minus 273. I don't know if they implemented this into this simulation. You see how they still vibrate at minus 267? I mean, the molecules still vibrate, but really, really slow. Let's try to go further down. Minus 270, 271, 272. Okay, let's see if it's gonna stop. It's supposed to stop. By the way, in nature, you can never go to absolute zero, but maybe they implemented it here. No, okay, minus 273. It stopped. Okay, they did that. That's fun. I actually didn't know, guys. I mean, I figured it out now, filming this video. All right, so this is all I wanted to say about the phases of matter and how temperature makes solids, actually makes molecules in a solid vibrate. And then in a liquid, they still vibrate, but they have a larger range of motion. And then in gases, they go crazy. There is no bound situation, and molecules are free to move. Okay, so this is it about this simulation. And let's go back to the notes. So we saw that the electrostatic potential energy between ions in a solid is less than 0 for bound materials, which are solids. Okay, and it's negative in the sense that we need to provide energy to break those bonds, which is exactly what we saw in the simulation. It's less negative, that's larger actually, okay? So less negative, like minus 10 is, sorry, minus 2 is a larger number than minus 10, okay? Remember that, because if we draw the number of, the number line, if this is 0, this is 1, this is 2, this is 3, and if this is minus 1, minus 2, and minus 3, for example, we see immediately how minus 2 is larger than minus 10, sorry, minus 3. So this is what I mean by larger, okay? So it's less negative, and therefore larger for liquids, okay, and practically 0 so V is about approximately equal to 0 for gases, so it's the largest actually, okay? So gases have the largest electrostatic potential energy in the sense that it's 0, and 0 is larger than a negative number, okay? This is a point of confusion usually for students, but I hope this makes sense, and I'm gonna move on, okay? And if something's wrong, guys, ask me in the comments. So another thing we saw is that as T increases, the kinetic energy also increases. And I'm talking about the kinetic energy of molecules, or atoms. And I use this interchangeably because, for example, copper is a solid, right? And copper only consists of copper atoms, whereas water, ice, is a solid, but it consists of molecules. But both of them follow the same principles. Like if I melt copper, and then if I evaporate copper, I will need a really high temperature to do that. But the same principles of thermodynamics apply to all these substances. Okay, I hope this makes sense. So as I increase the temperature, I increase the kinetic energy of molecules. Another thing you need to know in thermodynamics is that temperature always flows from hotter to colder objects. This is sometimes called the zeroth law of thermodynamics. Another thing we need to define is that there is a lower bound of minus 273.15 degrees Celsius, or also known as 0 degrees Kelvin for temperature. So if someone tells you that the temperature of an object is minus 300 degrees Celsius, they know nothing about physics. There is no upper bound, by the way. Nothing that is known, at least for now, okay? So theoretically, we can have infinite temperatures, but I doubt it. There's probably a limit that we don't know about yet. But stars get really hot, guys. So temperature can get really hot, but not very cold. It can go as cold as minus 273.15 Celsius. Now, 0 degrees Celsius is 273.15 Kelvin. So in any degree Celsius, we add 273.15 to get the degrees in Kelvin. And I advise that always use kelvins in A-level physics, just to avoid confusion. Better safe than sorry, they say, and so on and so forth. All right, this is all I wanted to talk about related to temperature and heat and stuff like that. Now let's go talk about heat transfer, which is the next topic. So heat transfer. Okay. Now, we saw how inside objects, molecules or atoms vibrate. So we can model this as something like this. Maybe these are 3 atoms, and you can picture these interactions as springs that allow the motion of particles. Okay, so this is how heat is transferred pretty much. Okay, because things vibrate and heat is transferred pretty much. Okay, now different materials have different molecular structure. Meaning that these springs that I showed you will have a different spring constant, etc. I mean, there are no springs. It's just an analogy. It's just an abstraction of how interatomic and molecular interactions work, okay? So different materials have different molecular structure. So transferring the same amount of heat will not raise the temperature of the material by the same amount. What I'm trying to say is that if this is indeed, I mean this, then the spring abstraction. So if this is if this is how things behave internally, then if I have larger atoms, okay, of a different substance connected by the same springs, okay, if I give the same amount of heat, and what is heat energy? If I give the same amount of energy to these larger and heavier molecules, the whole thing is gonna move by a little, right? So the temperature will not raise by a lot, like in this first substance. So this is the substance 1 and substance 2, okay? So in substance 1, if we transfer some heat, these guys are going to start vibrating really violently, whereas in substance 2, the same amount of heat will not make them vibrate by too much, okay? So this is modeled by this equation, which you need to know, and it's provided, you need to know how to use actually, and it's provided to you in the back of the paper. So the heat transferred to a material, heat transferred measured in joules, is equal to C times M times delta theta, okay? Let's go define these quantities. We already defined what delta E is the heat transfer to the material. C is the specific heat capacity. This is how it's called, specific heat capacity. It differs between materials and phases, okay? What do I mean by that? So the specific heat capacity of copper will be different than the specific heat capacity of ice. But then the specific heat capacity of ice is different than the specific heat capacity of liquids, of water pretty much, okay? Mass is the mass of the substance. C is measured in, before we talk about the mass, is measured in joules over kilograms over degrees Celsius, or joules over kilograms over kelvins. Okay, so that's K. Mass is the mass of the substance, so M is the mass of substance in kilograms, and delta theta is equal to T final minus T initial in degrees Celsius or Kelvin. I know I told you to use kelvins, but in this case, because we subtract the temperature from a temperature, we can use Kelvin safely. Okay, so the same change of of temperature in Celsius is the same as the temperature change in Kelvin. Okay, because that 273 is subtracted pretty much. Okay, but to be safe, it's better to use kelvins. Now, you can think of C. I want to talk a little bit more about C because it's important. So C can be thought of, the specific heat capacity can be thought of the specific heat capacity can be thought of as the energy needed to raise the temperature of 1 kilogram of a substance by 1 degree Kelvin or Celsius. So I'm gonna write Kelvin. What do I mean by that? Let's use a new page. So low specific heat capacity means that we have a good conductor of heat. These are your metals, for example. Metals have a low specific heat capacity. We can provide a very little heat and they heat up really fast. And then high specific heat capacity means a bad conductor of heat. Okay, bad conductors of heat are usually also bad conductors of electricity. So for example, diamond. You can provide a lot of heat and it's not going to heat up, okay, because it's a bad conductor of heat. And this is something I already mentioned, but different phases, meaning solid, liquid, or gas of the same material, have different different specific heat capacity. And I'm going to provide the example of water. So specific heat capacity of ice is 2,200 joules times kilograms to the minus 1 times kelvins to the minus 1. The specific heat capacity of water is higher, is 4,200 joules kilograms to the minus 1 times kelvins to the minus 1. And then the specific heat capacity of steam is also different, and it's 1996 joules, kilograms to minus 1, kelvins to minus 1. And let me give you, so you see how it's the same substance, different phases, different specific heat capacities. And then let's see 2 more examples. So specific heat capacity of aluminum is 910 joules per kilogram per Kelvin. And for gold, C of gold is 130 joules per kilogram per Kelvin. Okay. So when you provide heat to a material within the same phase, the temperature changes. Now, the next topic is specific latent heat. Okay, this definition has to do with phase changes. So this is the energy required for 1 kilogram of a material or a substance to change phase. So when we dealt with specific heat capacity, we were dealing with heat transfers within the same phase. So we increase the temperature of water and the temperature of water, we provide heat to water and the temperature rises, but it's still water, okay? When we deal with specific latent heat, we are interested in changing the phase. So we go from liquid to gas, from gas to liquid, and so on and so forth. So when a liquid becomes a solid, we call that specific latent heat of fusion. Why is that? Because the liquid fuses together to become solid, okay? But when a liquid becomes gas, we call that specific latent heat of vaporization. I hope this makes sense. We quantify all these using this equation. So this is the energy we provide in joules. So delta E is delta M, the mass of the substance in kilograms, times L. Okay, L is the specific latent heat, and it's given by joules times kilograms to the minus 1. Or we can also use M times L. And let's go see some example values. So for water, L fusion is 330 kilojoules per kilogram, whereas L vaporization is 2.6 megajoules per kilogram, okay? So this is for water. So what does this mean? We need to provide, for 1 kilogram, to turn 1 kilogram of water into 1 kilogram of steam, we need to provide 2.6 megajoules. On the other hand, if we have 1 kilogram of water that turns into 1 kilogram of ice, 330,000 joules are released, okay? So this is what it means. And notice that in this equation, delta E equals to delta M times L, there is no temperature involved. Why is that? Because there is no temperature change. There is no temperature change during a phase change. This is important. Okay. All the energy during a phase change goes into breaking the bonds of the material. Effectively raising the potential energy U. Okay. Is there anything else I want to mention here? So when a liquid turns into a solid, there is no temperature change. So the water stays, for example, at 0 degrees Celsius until all water turns into solid. And the same happens at 100 degrees Celsius. Okay. So if we plot this into, if we make heat curves, so if we plot this, we will see that if we use the example of water, so if this vertical axis represents the temperature in Kelvin, and the horizontal axis represents the change in energy in joules, then we see that if this is 0 degrees, actually, since I used Kelvins, I have to write 273 K here and 373 up there. Okay. So if we increase, if we provide some heat, we increase the temperature of ice. So the gradient there is going to be 1 over C ice. Okay. So in this region pretty much, okay, we have delta E is equal to delta M C times delta theta. Okay. But then this flats out. So this is the area where ice turns to water. So here we apply delta E is M, so delta M times L. Okay. If we keep providing energy, the temperature of the water will start rising again. Okay. So this is the gradient of this curve is going to be 1 over C of water now. Okay. And then if we keep providing energy, we will vaporize this water. So water turns to gas. And now I run out of space, but this is gonna start changing again in a straight line. And this gradient is gonna be 1 over C of steam. Okay. So phase changes happen here and here, whereas in here, here, and here, we apply delta E equal to C times delta M times delta theta. Okay. And that's it for heat transfer.